All right, today we're tackling one of the biggest, most fundamental challenges in quantum computing. Seriously, this is a big one. It's basically a story about a massive tug of war, a clash of titans, if you will. On one side, you have the dream of a perfect universal toolkit. And on the other, well, you've got the universe itself, laying down some pretty strict rules about how to keep things safe.
So, what if the perfect toolkit, the one you need to build a quantum computer, was fundamentally impossible? Just think about that. Imagine you have the ultimate Lego set, right? A kit that lets you build anything you can dream of. But here's the catch. What if just using those perfect bricks made whatever you built super fragile? Like it could just crumble at any moment. That, right there, is the core dilemma we're up against in quantum computing. And it's a huge hurdle, maybe one of the biggest, standing between us and the quantum future we're all working towards. Okay, so to really unpack this whole thing, we've got to start with the toolkit itself. What even is it? Well, in any computer, doesn't matter if it's the one on your desk or a futuristic quantum one, you need a basic set of operations. We call them gates. Think of them as the fundamental verbs, the actions you can combine to do any calculation you can imagine.
So let's make this a little more real. Could you build every single computer in the world with just one type of switch? It sounds crazy, right? But in the world of classical computers, the ones we use every day, the answer is, yeah, you totally can. And it's an incredible thought, isn't it? That one single, simple little component can be the bedrock for all digital complexity. This idea leads us to a really powerful concept.
And that concept is called functional completeness. Now, I know it sounds a bit academic, but all it really means is that your set of building blocks is universal. If your set of gates is functionally complete, you can wire them together in all sorts of clever ways to create any other logic gate you could possibly need. It means you've got it. You have the universal toolkit. You know, there's this great analogy that I think just nails it. It goes something like this. To say that a NAND gate is functionally complete is like saying that you can live in a brick. Of course, you can't live in a single brick, but you can build a house out of those bricks and live in that. A single NAND gate isn't a computer, but because it's a universal building block, you can piece together enough of them to build any digital house you want.
And here's that exact power in action. Check this out. Just by wiring two of these NAND gates together in a certain way, poof, you've made a totally different gate, an AND gate. And if you can do that, you can do anything. With enough of these simple little building blocks, literally any classical circuit is possible. Now that is a universal toolkit.
So, okay, that's the classical ideal, right? Nice and clean, but the quantum world, it's not nearly that neat and tidy. In fact, quantum computers have this fundamental weakness, a real Achilles heel that threatens to bring the whole thing crashing down.
So what's the problem? It all comes down to qubits. They're the building blocks of quantum information, but they are unbelievably fragile. The slightest little vibration, a tiny shift in temperature, what we just call noise, can completely knock them off course. This process has a name, it's called decoherence, and it's basically like a wave of static that just washes over your calculation, corrupting all your data and wrecking everything.
So how in the world do you fight back against all that noise? Well, our main weapon in this fight is something called quantum error correction. The big idea here is pretty simple, actually: redundancy. Instead of putting all your eggs in one basket, storing your information on one super fragile qubit, you spread it out. You encode it across a whole team of what we call physical qubits. That way, if one little qubit gets hit by an error, the rest of the team can work together to protect the original logical message. It's like having backups. But of course, that creates a whole new problem. If all your precious information is bundled up nice and safe, how do you actually do anything with it? How do you perform calculations on it without having to unpack it and expose it to all that noise again? Well, you need a very special kind of operation. The goal, the absolute dream, is to be able to run your logic gates directly on that encoded protected data. You want to keep the shield up always. Because think about it, if you have to decode your qubit just to do a calculation, you've just thrown away all the protection you worked so hard to build in the first place. And the most elegant, beautiful way to do this is with something called a transversal gate. And it really is a clever idea. Here's how it works. You take a simple physical gate and apply it to each of the individual qubits in your encoded block all at the same time, in parallel. It's just so clean. And this is what we mean by the perfect shield, because it basically guarantees that a single error on one qubit can't spread like a virus and contaminate the rest of your system. It keeps errors contained.
It's naturally, beautifully fault-tolerant.
Okay, so now we have our goal, right? A universal set of gates that are also transversal, meaning they're perfectly safe. It seems like the obvious path forward. But then, 2009 happened, and a theorem came along that basically threw up a giant, unavoidable roadblock right in the middle of that path.
This is the famous Easton-Kinnell theorem, and it's what we call a no-go theorem, which is basically the universe's way of saying, nope, you can't do that. What it boils down to is this. A universal set of quantum gates needs to be able to do all sorts of complex, continuous operations. Think of a smooth, fluid rotation in any direction. But transversal gates, they're much more rigid and discrete. They act on each qubit one-to-one. And what the theorem proves, mathematically, is that these two properties just don't mix. They are fundamentally incompatible.
So here it is, the fundamental conflict laid bare. On one side, you have universality. That's your universal toolkit. You absolutely need it to build any quantum algorithm you can dream up. But on the other side, you have transversality. That's your perfect shield. And you desperately need that to run your algorithm without it just getting obliterated by noise.
And the punchline from the Easton-Kinnell theorem is just devastatingly simple. You can't have both. You cannot have a set of gates that is both universal and fully transversal. Your perfect toolkit and your perfect shield, they're mutually exclusive. The laws of physics just won't allow it. Now, that sounds like game over, right? A total dead end. But this is where the story actually gets really, really interesting. See, a no-go theorem doesn't stop scientists. It doesn't make them give up. It just forces them to get incredibly clever. And this is a super important point. The theorem doesn't say fault-tolerant quantum computing is impossible. Not at all. It just says that the easiest, most elegant way of doing it, well, that's not going to work for every single gate you need. You can't have your entire toolkit be perfectly shielded. But maybe you can find a clever workaround for just the few special tools that don't fit in the safe box. And that is exactly what researchers have spent the last decade plus doing. It's led to this whole zoo of unbelievably ingenious techniques. The basic strategy is to build a sort of hybrid system. You do most of your work with the safe, easy transversal gates, but then, for those few tricky gates you need to achieve universality, you pull out one of these special tricks from your back pocket. So let's just take a quick look at one of these, magic state distillation. It's a pretty wild idea. Think of it like this. Instead of doing a dangerous operation directly on your precious protected data, you do it somewhere else, offline, on a special resource qubit. Then you take that resource and you purify it. You distill it until it's almost perfect. And then you use some quantum weirdness to essentially teleport the effect of that operation onto your data, all without ever dropping its shield. It's complicated for sure, but it's an absolutely brilliant loophole.
So in the end, the Easton-Kinnell theorem isn't really a story about impossibility at all. It's a story about how constraints, how rules, force creativity. It pushes us to build smarter, more complex, and maybe even more interesting machines. And so the huge question that we're left with is this. Which of these incredibly clever tricks, or maybe one that hasn't even been discovered yet, is going to be the one that finally unlocks the door to a truly powerful, fault-tolerant quantum future?